Let me introduce you to another great simulation by PhET. This one's called the moving man. It covers the basic vectors, displacement, velocity and acceleration. If you're feeling confident, you can go straight to the website yourself, download the simulation, play around with all the buttons, teach yourself in fact. That's just what I did. But if you're not feeling quite so confident, why don't you come with me and I'll take you through it step by step. If you're ready to go, we'll get started right now.
Let's look at displacement first. When we investigate motion, it's very important to define clearly where the moving object is at any given time. So here's our man stood on a giant ruler, with positive values on the right, negative values on the left. We can use this scale to define the position of our man at any given time. At the moment, he stood on the 0 mark, so let's change that. Let's take 4 1-meter steps to the right. So that's a change in position, or more commonly, a displacement. And it's in the positive direction. So we can say the change in position is equal to the displacement, or mathematically, S equals plus 4 meters. Now let's ask him to take a further 6 1-meter steps to the left. We now see that his total displacement is minus 2 meters. This is because he's only 2 meters to the left of his starting point, even though he's travelled a total distance of 10 meters. This is the important thing to understand about displacement. It's how far away he is from the starting point at any given time, no matter how far he travelled to get there. Displacement is a vector quantity. This means it has both magnitude and direction. So when we write S equals minus 2 meters, we mean there is a displacement of 2 meters to the left. We can present displacement information most usefully on a graph or chart. Here are the axes for my first displacement time graph. I'm going to drag the man towards the right at a fairly low steady speed. Just pause and think, what kind of graph do you think I'll get? Did you get it right? It's fairly steady. Now I'll drag him towards the left, a steady speed again, but faster this time. I'm going to end up beyond his starting point, somewhere near the tree. What will you see on the graph now? I got a nice straight line, but it's steeper than before and it's sloping in the opposite direction. It's got a negative gradient. Keep these ideas in your head as I introduce a new graph. Now I've introduced a velocity time graph. So what's velocity? It's often confused with speed. The speed of an object tells us how fast it's going. Distance divided by time. For instance, 20 meters per second. Velocity, however, is displacement divided by time. This means that the direction of travel is important again. Velocity is a vector. Consider this example. Instead of dragging the man, I can set our man's velocity at a constant plus 2 meters per second in this box here. When I press the start button, he will begin his journey across the screen. I want you to predict the shape of the two graphs. Are you ready? Here he goes. As I hope you predicted, the red velocity time graph is very simple, showing a constant 2 meters per second throughout, but notice in the positive direction, of course. The blue graph shows displacement increasing steadily with time. Let's take a closer look at these graphs. If we consider only the first 4 seconds, this green arrow represents the displacement over this time. It looks like it's about 8 meters. If we add another arrow to represent the time of 4 seconds, we now have the rise and the run for our graph, and we can use these to calculate the gradient or slope of the graph. So the gradient of our position time graph is rise over run, which is displacement divided by time, which is the velocity. So for our little man, his velocity is 8 divided by 4, or 2 meters per second, which of course is exactly what we put in the red box at the start. Make sure you've absorbed all this before we go any further. If we look at the red graph, we can get some further information. Over the 4 seconds of our experiment, the velocity was steady at 2 meters per second. Now if we take our equation and rearrange it like this, we can see that the displacement is equal to the velocity multiplied by the time, or 2 times 4 in this case, which is 8 meters, which is, of course, the displacement we discovered earlier. But if you look closely, you can see that this value is also equal to this area under the red graph. And although this is a very simple graph, this is true of all velocity time graphs, no matter how complicated the shape. The area under a velocity time graph at any given time is always equal to the displacement. So now I've added a third graph, an acceleration time graph. Most students find acceleration the trickiest of our 3 vectors. For instance, when I say an acceleration of 1 meter per second means that the velocity is increasing by 1 meter per second every second, it's not crystal clear. I'm going to use the simulation to try and get that idea across. I'm going to set the acceleration here at a constant 1 meter per second. So when I press the start button, what will the 3 graphs look like? Are you ready? Here we go. Well, when we look at the blue graph, we can see that the displacement no longer increases in a steady fashion, because the velocity is not constant. It's getting bigger and bigger as the man accelerates. At the beginning, here for instance, the gradient is small, indicating a small velocity. As shown here. What's that, about 1.3 meters per second? Towards the end, we have a bigger gradient, which means a bigger velocity, as we see here. That's about 3.7 meters per second, I think. So how do we get the velocity from the blue line if it's a curve? Well, the velocity at any instant can always be obtained from the gradient. It's only a little more complex. We now have to draw a tangent to the curve at that point and then find the gradient of that, still using rise over run in the same way. The red graph shows a steady increase in velocity over time because the acceleration was constant. The slope or gradient of this graph is equal to the change of velocity divided by the time, which is equal to the acceleration. We can check this out by finding the rise over the run for the first 4 seconds. As we already knew, the acceleration is confirmed at 1 meter per second. So now it's time to be a bit more adventurous. Here's a more challenging example, and if you can understand this, you've made excellent progress. The acceleration will be a constant 1 meter per second exactly as before. But, as you can see, I've set the original displacement at plus 10 meters, and its original velocity will be minus 5 meters per second. That means he will start off moving in the negative direction, to the left. So, when I press the start button, what will happen? Give yourself a good few seconds to think about it. Then when you're ready, here goes. Okay, Let's try and interpret that. Remember, the graphs are all linked because they each tell us something about the motion of the man. The green graph tells us that the acceleration was a constant 1 meter per second. This caused a steady increase in the velocity. It started off with a big negative value, minus 5 meters per second. This increased up to 0, then continued increase into about plus 5 meters per second by the time he hit the wall. What about the blue graph? Think only about the displacement for a moment. It went from a positive value to a negative value, and then back to a positive value again. Just take a moment to absorb that. Is that what happened in the video? Next, notice the gradient of our position time graph. It's negative here. This means the velocity was negative. The man was moving to the left. And this is confirmed here, a negative value on the red velocity time graph. If you look at this point, the slope is 0. That means the velocity is 0, and the man stopped for a brief instant. Do you remember that? If you look here, it's true. And finally here, we have a positive slope, indicating positive velocity. He was moving to the right now, which is confirmed here. Remember, you can stop the video anytime if you need to have a good think. Actually, here's something better. Let's have an action replay. Let's watch it again. This is really useful for having a close look at both the magnitude and direction of the vectors involved. Let's start with velocity. You can see a red arrow appearing pointing in the negative direction because it represents the initial velocity of minus 5 meters per second. But just watch what happens to that arrow as the simulation progresses. It's minus 5, then minus 3, minus 1, 0 meters per second, then plus 1, plus 3, and about plus 5 when he slams into the wall. Acceleration next, a green arrow in the positive direction representing 1 meter per second, plus 1, plus 1, plus 1, all the way through. But just watch what happens when he hits the wall. Did you see that? For a brief instant there was a massive arrow in the negative direction, representing a massive deceleration when he hits the wall. The velocity fell from about 5 meters per second to 0 in almost no time at all. Okay, one last chance to watch and think. It's really interesting to see the two vectors together. Think about how the green unchanging acceleration arrow affects the red velocity arrow, controlling what happens every step of the way. It looks complex, but all that's happening is that the velocity is steadily getting bigger and bigger. So first he slows down until he stops. Then he starts to get faster and faster again, but in the opposite direction, of course. Have a good think about this simulation and how all the graphs and vectors link and come together so beautifully, giving different aspects of the same story. It's important stuff.
I hope you got something out of that. Remember though, the best thing to do now that you've gone through that is to try the simulation yourself. Change all the variables, make predictions, run the simulation, and in no time at all you should have conquered this particular topic and you'll know vectors inside out. That's the hope anyway. Okay, I'll see you next time. Bye for now.